Okay, next we will do few problems from this section, groups and subgroups. So these are the exercise problems from Abstract Algebra by John B. Fraleigh. The question is determine whether the binary operation is gives a group structure on the given set. So there are 5 given sets, and we can do very fastly this. So we are considering the first question. Let star be defined on Z by letting A star be equal to A into B. So our question is Z. Actually, this is dot product. Z dot is a group or not. But we know that if 2 belongs to Z, then 2 into 1 by 2 equal to 1 by 2 into 2. So the inverse of 2 is 1 by 2. But 1 by 2 doesn't belongs to Z. So the inverse of an element in Z doesn't belongs to Z. So it is not a group. Not a group. Similarly, you take the second one. The second question is, let star be defined on 2z, 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 that is set of all positive integers, and a star b is a plus b, addition in two positive integers. So for 2, our set is 2z and binary operation is plus. Actually, if we add two even numbers, we will get the result will be even number. Therefore, it is closed under plus. And also, we know that plus is associative binary operation, and also identity element. We know that 0 can be written as 2 into 0. Therefore, 0 is an even number that belongs to Z. So, the identity is in Z. And also, for any element, A belongs to 2Z, we have A is of the form 2 into some m, that is even integer. Then we have minus A, which is in minus 2m, must be an even integer. So A plus minus A, which is equal to A, 2m plus minus 2m, which is equal to 0. Therefore, the inverse is also exist in this set. Hence, the second one is group. This is group. And third one, a star b equal to root of ab, and it's defined on set of all positive real numbers. Now, we can check the associativity property. So, if we take a star for third question, a star b star c, then this is actually is equal to root ab star c, which is equal to root of root ab into c. But a star b star c equal to actually a star root bc, which is equal to root of a root bc. These two are not equal. These two values are not equal, therefore not associative. The binary operation is not associative, therefore not a group. And also in third set of all non-zero real numbers, the binary operation is division. So division is not also associative. Division is not associative, therefore it is not a group. This is also not group. Not group. And fifth one is defined on star is defined on C, set of all complex numbers, A star B equal to mod AB. Now if you take minus 2 belongs to C, and we need an identity element. So suppose minus 2E star E, which is equal to modulus of minus 2E. Mod value is always positive, that is 2E. So this is always greater than 0. Therefore, E cannot be the result there does not, this cannot be equal to -2, cannot be equal to minus, so there does not exist identity element. E doesn't exist. Therefore, this is not a group. So only second one is the group. And when we move to the second problem, this is very important problem. Show that if G is a finite group with identity element E with even number of elements, then there is an element A equal to E in G such that A star, then there is an element there is an element A in G. It's not A equal to E. A in G such that A star A equal to E. That means A inverse equal to A. There is an element A belongs to G such that A inverse equal to A. So we have to show that. So I'm taking a set, let S be a set of all A such that A belongs to G, our group G, such that A equal to A dash. That means A equal to A dash. Okay. Then this set S sorry, A not equal to A dash. A not equal to A dash. That means there is no inverse. That means A is not inverse. A and A, that means A is not inverse of itself. So S is set of all A belongs to G, that then S contains even number of elements. Even number of elements, because if A not equal to A inverse, then if B is inverse of A, then B must belongs to S. So this S contains even number of elements. Okay. Now we have E is identity element, E star E equal to E, right? So E doesn't belongs to S, but E belongs to G because G is a group. Now, if and also given that G has even number of elements, even number of elements. Therefore, therefore, G minus S. S is set of all A belongs to G such that A not equal to A dash, that is yours. And G and S has even number of elements because S contain even number of elements. Therefore, G minus S has even number of elements. Since E belongs to G minus S, then there must exist at least one A belongs to G such that A star A equal to E, because E belongs to G minus S. So one element is in G minus S and G minus S is E1. Therefore, it's not E alone. There must exist another element A belongs to G such that A star A equal to E. Therefore, this is shown. That means if G is a finite group with the identity E and with even number of elements, then there is an element A in G such that A star A equal to E. So hence the proof. Now we will do another problem. Show that every group G with identity element E such that x star x equal to E for all x belongs to G is available. That means G is a group and every element in G, every element x in G, we have x star x equal to E. So that is the condition given. Every element Every element of G is the inverse of itself. That means if x belongs to G, then x star x equal to E. Now we have to prove that G is abelian. So that we have to prove. So for that, we have given an hint. Consider AB belongs to G, then clearly A star B belongs to G. Now we are taking A star B is a number, is an element in G. Now A star B is an element in G, then A star B must be equal to E, because by the condition any element in G must be of the form their star product, or by applying the binary operation of that element must be identity. Now we will take the letter, and now let A dash and B dash be the inverse of A, B respectively, because uh, since G is a group, A, B belongs to G, inverse exists. Then I'm calling this equation number 1. Now what we will do is I'm multiplying both sides. That is A star B star A star B equal to E. What I am doing is I'm multiplying here A dash star. So similarly, it is equal to A dash star here, and I'm multiplying uh, uh, sorry, I'm multiplying A not A dash star. So sorry, I'm not taking the inverse. Sorry. Sorry. So what we will do is A star B star. So I will erase this. So we are considering here. We are considering here A star B star A star B equal to. Now I am multiplying A on both sides. A star B star A star B, and I am here multiplying with the B, which is equal to. I am multiplying on both sides A E star. So I'm multiplying with A, here I'm multiplying with B, here I'm multiplying with A, B. Now A star, that is A star A by associativity property, B star, and B by associative property, A star B equal to A star E star B, that is equal to A star B, because E is. Now A star A equal to E, that is E star B star A star B equal to E, because any element if we take from G, X star X equal to E. So this is A star B. Now E star B is B itself, star A star is so A star B, A star B is equal to B star A. For all A, B belongs to G, therefore G is abelian. Thank you.